Recording started.
I'd like to welcome you to this recording of another lecture on the application of theorems 418 and 419, steady mass flow. In this recording, we will look at at some further examples. The first example is that of sample problem 4.8 in edition 6, or sample problem 4.9 in edition 7. Here we have an aircraft of mass M which is flying. There's an axis system attached to the aircraft. The x-axis points forward and the y-axis is normal to the plane of the aircraft. It's given that this aircraft is flying at a speed of v in the positive x direction, which means that it's flying at an angle theta with the horizontal. It's, in other words, climbing at this angle theta. It's a jet aircraft and it has an air intake. Of course, the aircraft engine powers the aircraft by having combustion of fuel with air. So there's an air intake. This is indicated by these green arrows. And the mass flow of the air intake is given as m sub a prime kilograms per second. It also has an exhaust mass flow rate of m sub g prime. Now this differs from m sub a prime because of the fact that fuel is mixed with the air. So the mass flow at the exhaust is actually larger than the mass flow of air due to the additional mass flow coming from the fuel. And it's given that the fuel mass flow is m sub f prime, kilograms per second. Now getting back to the exhaust, it's given that the exhaust has a velocity relative to the aircraft such that the magnitude of this relative velocity is u. That is indicated by the exhaust mass flow and velocity is indicated by the green arrows at the back. Furthermore, it's given that the aerodynamic forces acting on the aircraft is the lift L, which is indicated by this arrow, and the drag D, indicated by this arrow D. Now, here you should bear in mind that actually there's, you can think of it that there's but a single aerodynamic force acting on the aircraft of some other magnitude and in some other direction, which may not be known. But it's conventional in aeronautics to always break this single aerodynamic force, or maybe you can call it the resultant aerodynamic force, up into to break it up into two normal components: the drag, which is always defined as in exactly the opposite direction in which the aircraft is flying. So the drag vector will always be exactly in the opposite direction as the velocity vector v of the aircraft, this vector indicated with a green arrow. And then the lift is always normal to the drag, or normal to the velocity vector. Furthermore, since this aircraft is flying in a gravity field, it's indicated here that there's also another force vector playing a role, namely the weight of the aircraft, which is merely the mass of the aircraft times g. Now what they ask us to do is to determine the equations of motion of this aircraft as it's flying at a constant speed, and then the thrust T delivered by the engine or engines of this aircraft. Now, if we now turn to vector notation, we can say that the exit velocity of the exhaust relative to the aircraft, that was given to us as a magnitude of u. But since it's in the negative x direction, we can, as a velocity, label this relative velocity as minus ui. Its magnitude is u, but its direction is in the negative x direction. So we therefore say this is minus ui. And you should understand this is the velocity of the exhaust gas relative to the aircraft. That's indicated by these two subscripts. Now, if we try to now calculate the absolute velocity of the exhaust gas, this we can do using the relative velocity equations that we've actually used in chapter 5. So we can say the absolute velocity of the exhaust gas is equal to the absolute velocity of the aircraft plus the velocity of the exhaust gas relative to the aircraft, all as vectors. Now, the absolute velocity of the aircraft is shown here. It's v in the x direction, so that is just v times I. And then the relative velocity of the exhaust gas relative to the aircraft, we have just now calculated that as minus u times I. So we need to add that, and if we do, then we can say that this shows us that the absolute velocity of the exhaust gas is v minus u times I. Now, I need to point out that I'm busy solving this problem using the absolute velocity of the exhaust and the absolute velocity of the inlet flow into the aircraft, which is not the same as what the book is doing. The book is solving this problem using the relative velocity of the inlet into the aircraft and the relative velocity of the exhaust out of the exhaust of the aircraft. And one can actually do it the way that the book is doing it. I'm not claiming that the solution of the book is incorrect. However, we have, in the whole of chapter 4, always worked with a fixed axis system. And I'm not using this XY axis system to solve the problem. I'm solving the problem in terms of another axis system which is fixed to the Earth. And therefore I'm using the velocities in an absolute sense with respect to the Earth fixed axis system, merely to stay with the convention that we've used throughout our presentation of chapter 4. So what I'm presenting, you can think of this as an alternative solution to the one in the handbook, where they use relative velocities rather than absolute velocities to solve the problem. But I'm going to use absolute velocities, and because of that I've now calculated the absolute velocity of the exhaust gas in an Earth fixed axis system. Okay, so I'm clearly going to apply equation 418, and that is the reason why I've calculated the exhaust gas velocity. So let's, perhaps I should have done that earlier. Let's just consider what is our system. Our system here is the aircraft, and just the air inside the aircraft, in the engines. In other words, the exhaust port of the aircraft, you can think of that as the exit cross-sectional area of our steady mass flow system, and the cross-sectional area of the inlet which sits just above the wing, just behind the cockpit window. That is the inlet cross-sectional area of our steady mass flow problem. Using equation 418 means that we need to calculate the vector difference between the exit velocity and the inlet velocity, and the way that we've normally done it in terms of absolute velocities. And because of that, I've now calculated the absolute exhaust velocity. This is now known, so I next need to calculate the absolute inlet velocity. But the absolute inlet velocity is a zero vector because the air is actually stationary, absolute. If you look at the velocity of the air in the Earth fixed axis system, the air is standing still. The aircraft is moving through still air. And because of that, we can say that the inlet velocity is a zero vector. Now, in general, we're going to apply the equation as we've derived it, equation 418. But in this case, we will also have a summation on the right-hand side. So in this case, the equation will really look like this. And the reason for that is that we really have two mass flows on the right-hand side. We've got the mass flow of the air through the aircraft, but we also have the mass flow of the fuel. And we need to take the mass flow and momentum change of both these mass flows into account. And because of that, we simply have a summation of m prime delta v's on the right-hand side of our equation. Now, let's first look at the first term in this summation, namely the one pertaining to the mass flow of the air. The the delta V vector for the air, in other words, the vector difference between the exit and inlet velocities for the air, will simply be the difference between the two velocities just now calculated on the previous slide. In other words, the absolute velocity of the exhaust minus the absolute velocity of the inlet. Now, the absolute velocity of the exhaust was calculated as V minus U in the I direction, minus a zero vector, and the result is, in other words, just V minus U in the I direction. So that is the delta V for the air. And if we now calculate the same for the fuel, of course the fuel burns with the air, and after this combustion, one cannot really distinguish the fuel from the air, but at least we can say that the fuel particles after combustion, well, it's not fuel anymore, it's then oxides and various other exhaust gases, but that will be flowing out of the system at the same exhaust velocity as the air. But the inlet velocity for the fuel would be the velocity of the aircraft, because the fuel is actually traveling with the aircraft. One should, in a certain sense, consider the fuel in the tank as not part of the system, although this is not a perfect way of looking at it, because if we do, we should really subtract the weight of the fuel in the fuel tanks from the weight of the aircraft, which we are not going to do. So this is a small approximation. But in any case, if we consider the fuel in the fuel tank as not part of the system but traveling with the system, we can say that the fuel is entering our system at the velocity at which the aircraft is flying, because of course the fuel tank is moving at the same velocity as the velocity of the aircraft. The fuel in the fuel tank already has the momentum associated with the velocity of the aircraft. And so therefore we need to subtract to calculate the delta V of fuel, the velocity of the aircraft, which is simply a positive V in the I direction, but the minus here comes from the fact that we subtract it. And if we then calculate this, we see that the delta V of the fuel is just minus U in the I direction. Now I've just repeated these two equations that we've calculated in the previous slide at the top of this one. And if we now go back to equation 418 in its modified form for this problem, it is given here, which means that we can now, on the right-hand side, have the mass flow rate of the air times the delta V of the air, which is what I have here. There's the mass flow rate of the air, and as identified earlier, and then the delta V of the air as we've calculated it and repeated it at the top here. And then we add to that the mass fuel rate identified earlier of the fuel in sub F prime, multiplied by the delta V for the fuel, which is minus UI. So that is the right-hand side, this summation over two terms on the right-hand side, the momentum change terms, if you wish. And then on the left-hand side, we need to include the resultant external force on the system. Now, if we look at the free body diagram that's drawn here, and note that I've modified the diagram in the book because I'm not using it for exactly the same purpose as for which it's used in the book. And by the way that the authors are actually using it in the book, I find a bit confusing, so I'd like to encourage you to perhaps disregard that figure in the way that it's in the book. The way that I've modified it, I've taken the red arrows that was inside these almost rectangular shapes. I've taken that out because there are not really forces acting on our system at that position. Well, you can perhaps also see, if you wish, this figure on the left-hand side is a free body diagram. It indicates the same forces. Now, if we look at this, we see that we can decompose the weight of the aircraft into a component in the Y and in another component in the X direction. And the component in the Y direction will be mg cos theta, and that will be in balance with the lift. So let me repeat again. In the Y direction, we've got the balance of forces, or equilibrium of forces. The component of mg in the negative Y direction will be in equilibrium with the lift L. And so we can therefore disregard the lift L and the mg cos theta y direction component, or negative y direction component of the weight. However, in the x direction, we have a summation of components. The x direction, or the negative x direction component of the weight, is mg sine theta in the negative x direction. That will of course add to the drag in the negative x direction. And that is what I have on the left-hand side of my force equation, minus mg sine theta. That's the negative x direction component of the weight, minus d, the drag, times I. So that is all the forces acting on the system. This is not only the forces in the x direction, because in the y direction we really have a zero force, because of the fact that we have equilibrium in the y direction. So this is really a first way of writing the equation of motion of the system. And we see that after we've now written it, that this equation has only components in the x direction. We can thus write this actually as a scalar equation by just multiplying this whole equation with the unit vector I to get a scalar equation, the forces in the x direction. And so that is what I've done here, but then I've also made a further simplification in that I realized that the mass flow rate of the exhaust gas must be the same as the sum of the mass flow rate of the air and the mass flow rate of the fuel. And if I realize that I've got on the right hand side the MA prime times V and the MA prime times minus U and the MF prime times minus U, I can combine those two as a single term, minus M sub G prime times U, and then all that's left on the right hand side is this term here, MA prime times V. I can furthermore multiply this equation with minus 1. I think I've just repeated this equation on the next slide, yes, but I can now multiply this through minus 1, and this is then the final form of the equation of motion of this aircraft system, as it is also in the handbook. Now, I can now identify this left-hand side of the equation, the mg sine theta plus d, as the thrust of the engine. Now, the description that is given in the handbook, I think, is perhaps a bit confusing, but I think the way to look at this is that if we remove the engine and the airflow through the engine from the aircraft, of course, what this equation really tells us, if I can just simply interrupt myself, is that we have a force, a resultant force on the aircraft system in the negative x direction. Its magnitude is mg sine theta plus d, and this force is associated with the momentum change in the negative x direction. You need to realize that that this term here, the mg times u minus ma times v, will always be positive. The magnitude of the exhaust gas relative to the aircraft is much larger than the actual forward speed of the aircraft. So this first term on the right hand side will always be larger than the second term on the right hand side. But this represents a very large momentum change in the negative x direction. And to have this large momentum change in the negative x direction, one needs the resultant force in the negative x direction. And that force can be associated with the weight component and the drag. It's almost as if we say that the drag and the weight component causes this momentum change. It's perhaps not perfectly correct to say that, but we can certainly say that it is associated with this. Now, we do not have equilibrium because we are accelerating air in the negative x direction. We cannot think of this system as a system where the forces are in equilibrium. However, if we take the engine, which is really the vehicle that's accelerating the air, if we take the engine out of the aircraft, and we take the accelerated air also out of the aircraft. And now, of course, you need to realize that in order to accelerate the air backwards, the aircraft is pushing on the engine, and the engine is pushing back on the aircraft with the reaction force. Now, that reaction force, we can think of that as T, the thrust. So if we take the engine and the airflow through the engine out of the aircraft, then we can, and only then, we can think of a situation of having an equilibrium of forces, where we have a thrust force, and I'm not particularly fond of actually even drawing the thrust force at the back here, because this thrust force actually acts at the point where the engine mountings are located, where the engine is mounted to the aircraft. But okay, let's live with the thrust force being indicated at the back. So for this, we have a force equilibrium where the thrust and the drag and the x direction or the negative x direction component of the weight of the aircraft is actually in equilibrium, just like the negative y direction component of the weight and the lift are in equilibrium. But in actual fact, if we look at the aircraft with its engine, this force does not exist. There isn't a force at the back of the aircraft pushing it forwards. The only forces that we have, when we think of the whole aircraft with the engine and the airflow through the aircraft, the only forces that we have are the three forces that's indicated at the upper sketch. We do not have a force pushing at the back of the aircraft. And we do not have equilibrium because the resultant of these three forces, you can think of that resultant is the force that is associated with the momentum change of mainly the air and also a little bit of the fuel passing through this reference volume of ours. So this is important that you realize that you should never try to solve these momentum flow problems with and by the way, this is also a statement that we made in sample problem 4.7 in edition 6 and 4.8 in edition 7, that green nozzle, also at the exit of the green nozzle there wasn't any force. In the same way we can say that there isn't actually any force acting on the aircraft at the back. It's only when we take the engine and the airflow out of the aircraft that we can conceive of a force, the thrust, that is really the force that the engine exerts on the aircraft. And then we can think of having equilibrium of forces. Okay, so enough of this. Let's move on to the next problem, which is problem 463 in edition 6, or problem 465 in edition 7. We have here a nozzle once again, which ejects air at a very high speed. The diameter of the nozzle is given as 40 millimeters at A, and the speed of the air as it issues the nozzle at A is 240 meters per second. So this is just slightly below the speed of sound, so it's not supersonic airflow, but it's quite close to that. This airflow then impinges on a vane. This blue thing here is you can think of that as a flat surface vane. It's actually indicated as OB because this vane hinges at point O to a fixed support. And the vane structure is such that it also has a lever going up with a counterweight, which is given as a mass of 6 kilograms, mounted at a distance of 240 millimeters from the hinge. The hinge, by the way, is given as at a distance of 120 millimeters above the center line of the airstream and in exactly the same vertical plane as the nozzle end. So in other words, the hinge O is right above the nozzle end. They give us that the density of the air outside the nozzle, in other words in the stream, is 1.206 kilograms per cubic meters. Now you can think of this in the way that if the air is not flowing through the nozzle, the vane will be in a vertical orientation, it will be hanging right in front of the nozzle. And as the air is now, let's say as some of the valve is open to allow the air to flow through the nozzle, the impinging air will, in a certain sense, push away the vein, and it will actually, if this is opened quickly, the vein will probably oscillate, and then the oscillation will die away, and then eventually it will come to a somehow other steady state angle, and they'd like us to calculate the angle theta. Now this angle theta will be determined by the steady mass flow problem. If the vein is no longer oscillating, then there's no acceleration, then we have a situation where we have steady mass flow, and then we can use the steady mass flow equations to solve this problem, to solve for the angle theta. Now once again, we're going to make the assumption here that the air stream over here is a cylindrical air stream. In other words, the cross-sectional area is circular, with a diameter of 40 millimeters, and then as this circular air stream hits the vein, we know that it will fan out and it will get thinner in practice. But provided that we look at it not too far from the point of impingement, we can actually make the approximation that the airstream remains a cylindrical airstream, and that the diameter also remains the same. This is not 100% true, but it's not a bad approximation, at least not for the first attempt to solve this problem. So we are going to assume, to solve this problem, that we have a cylindrical 40 millimeter diameter airstream over here, but also down the vein. Now I've redrawn, and I must admit my angles are not very nicely in agreement with the original sketch, but just live with me, a free body diagram which shows all the external forces acting on the system. Well, I must admit not all of them, because maybe I should make it complete. Let me quickly just do this. I may also have what I've neglected to draw here is the unknown hinge reactions at point O. I do not know what these two reactions, their magnitude, but I'm going to solve this problem by taking moments about point O. And if I do this, these two forces will not have a moment about point O, and because of that, neglecting them or not including them in the free body diagram will not cause me too much problems. So the only other external force acting on the system is this weight of the 6 kilogram mass, which is 6 times 9.81 meters per second square, 6 kilograms times 9.81 meters per second square, or in other words 6 times 9.81 newtons. And this is working at an angle theta relative to this arm of 0.24 meters. You should also convince yourselves this angle theta, of course, is that angle, which means that this angle here is the complement of theta, which again means that this angle is also the angle theta. Also note that I've selected perhaps a rather strange but a very useful axis system. The origin of my axis system is at the point O, the hinge, and I select an axis parallel to the vein downwards as my positive x-axis, and to the right downwards my y-axis, of course normal to the x-axis. So please take note of my x and y-axis. It's not in the direction that perhaps more commonly is used, but we are free, and you must always remember this, you are free to select the axis system in whatever convenient way is for you, if you find to solve a problem. If an axis system is given, you should perhaps be a little bit more careful when you do this, but if you clearly indicate that you do not use the axis system given, that is acceptable. But if an axis system is given and you do not specify in your own axis system, remember that your reader, and in particular the marker of your test or exam question, will assume that you're using the given axis system. Now in this case, the axis system wasn't given, so we can choose our own axis system, and the convenient one is the one that I've chosen here. Now, we will like to express our inlet velocity. Oh, maybe I should first just talk about my system. My system will then be the weight, the supporting bar, the vane, and the airflow from the entrance area at A, just as the air exits the nozzle. That's my entrance area to my reference volume, and my exit area will be some distance L along the vane measured from the point O. So I'm cutting through the stream at what I call point, some other point B. Well, it doesn't need to be exactly at B, but okay, we can think of moving B up or down along the vane, because I think I did use the subscript B later on to indicate the vectors. So my exit, the center of my exit area is this point here. I can label that as point B. And of course, since the stream is assumed to be 40 millimeters in diameter, this point sits at a distance 0.02 or 20 millimeters from B. I'm neglecting the thickness of the vane itself. So that's my exit area of my steady mass flow problem. Okay, let's move on then. Now, the entrance velocity in my steady mass flow problem is the velocity at A, and we know its magnitude is 240 meters per second. But we'd like to now express this as a vector quantity in terms of the axis system that we've used. And that is depicted by this little sketch. I've got VA, and it's making an angle theta with a positive x direction. That means that my x direction component will be 240 cos theta in the I direction, and the j direction or the y direction component will be this length, which will be 240 times the sine of the angle theta, but it will be in the negative j direction, because remember this vector is from the right to the left. So if I break it up in its x and y components, I'll have a positive x but a negative y component. Remember, my y-axis is going downwards to the right, whereas the y component of VA is upwards to the left. That gives me the minus j and the magnitude of 240 sine theta. My exit velocity at point B, now once again, if I assume the density remains constant through this, and that is a reasonable assumption, there's no reason why the density will change, because the stream is always at the same pressure, namely atmospheric pressure. So if the density doesn't change and the cross-sectional area of my stream doesn't change, it means that the speed of the flow at B must be the same as the speed of the flow at A, namely 240 meters per second. So my exit velocity is simply 240 I meters per second, the velocity at B. Since I'm going to use the moment equation, I need to calculate my position vectors at the exit and inlet areas, and maybe I should just draw these vectors. So my vector for the exit area, D sub B, will be the vector ending at point B and starting at point O. So it's this vector here. And clearly it has an x direction component of L, so it's L in the I direction, where I haven't specified what this L is, it's some other length. And it has a component of 20 millimeters in the y direction, or 0.02 in the y direction, so 0.02 j. So that is my vector dB from the fixed point to the center of the exit area. And if I now, okay, going on to the next slide, is erase that. But now my vector dA, the vector from my fixed point to the center of my inlet area, is in other words this vector here. And that vector is clearly making an angle theta with a positive I direction. Its length is 120, so its y direction component will be 0.12 meters times the cosine of theta, which is what I have here, in the positive j direction. And then its x direction component will be its length of 0.12 times the sine of this angle theta in the positive I direction. So that is my vector dA as I've drawn it here. So now I've calculated the inlet and exit velocities as vectors, the exit position vector, the inlet position vector. So I can now calculate the moments of the inlet and outlet velocities about point O. I also need the mass flow rate, and I'll calculate the mass flow rate in terms of the areas, densities and velocities that are known, namely at the cross-sectional area A. So it's rho A times A sub A times VA. Rho A is given as 1.206 kilograms per cubic meter. The area at A will be the radius of 0.02 meters squared times pi, and then the magnitude of the inlet velocity is 240 meters per second. So this gives me a mass flow rate of 0.36372 kilograms per second. Now, looking at the moment of external forces side of equation 490, I have the two external forces at the hinge O, which do not have a moment about point O. The only external force having a moment about point O is the weight, and the weight is 6 times 9.81, and its moment arm is really the length between this force and O, and that length will be 0.24 times the sine of this angle theta. It's that length times the sine of this angle gives me this length here. So this is my moment arm, this is the moment arm, the 0.240 times sine theta. And I see that with my x-axis and y-axis as indicated, my z-axis is coming out of the screen or out of the plane of the paper, or in other words, anti-clockwise is in the positive k direction. And so this moment about point O, the moment of this force about point O is clearly an anti-clockwise moment, so therefore I can say that the sum of the moments of all external forces is given by, if I multiply these numbers together, I get 14.126. So the sum of the moment of all external forces about point O is plus 14.126 sine theta k Newton meters. Note that there are no external forces acting on the vane in this region, where the air impinges on the vane. Let me just go back a couple of slides. Here are no external forces acting on the vane in this area. The only external forces in this system is the weight and the forces in the hinge. Okay, so I'm back to where I stopped. Let me now go to the next slide. So this is my equation 419 I'm going to apply now. I've calculated the left just now. I've calculated m prime. I have calculated the two vectors dB and dA, and I've calculated the velocities vB and dA. So I can substitute all of this into this equation. The sum of the moments on the left-hand side as given here. On the right-hand side, the mass flow rate that was calculated, and then dB containing the unknown distance L, and on the second cross product, the moment of the inlet area, I don't have any unknowns. So if I look at this, I see that this component L only appears in the cross product with the velocity in the I direction. And because of that, the cross product of this component with the velocity is 0, because it's the cross product of two parallel vectors. And with this, the unknown length L disappears from my whole equation. It falls away. It doesn't contribute to the solution in any way. Also, I can see that if I do the cross product of the dA with VA, I end up with the products of sines and cosines, where I've got I cross I's or J cross J's, which fall away, and the only terms that I'm left with is sine squared and cosine squared. If I simplify this whole equation, it ends up to give me this. It's just a matter of algebra. And looking at this result, I can see that the sine squared theta plus cosine squared theta gives me a value of 1, which really removes the presence of the angle theta from the right-hand side of my equation. So the right-hand side can now be calculated as a single numerical quantity times k, of course, and I can see here that I only have components in the k direction. So I can just multiply or calculate the dot product of this whole equation with k, with the unit vector k, to get rid of the unit vector k, to give me the scalar equation that I have here. And from this I can then solve for the angle theta as 38.17 degrees. That was what was asked. Now let's look at the last example. This is problem 4110. This appears, the same problem number is used in both editions, but in edition 6 it appears on page 326, in edition 7 on page 320. It's in the revisionary problems at the end of chapter 4. What we have here is a rather large centrifugal water pump. This pump is pumping fresh water at 20 cubic meters per minute. Fresh water means immediately that the density of the water is 1,000 kilograms per cubic meter. So the volume rate of flow is 20 cubic meters per minute. It is given that the inlet and exit speeds into the pump through the flanges at A and B. B is the inlet flange, A is the outlet flange. The speed at those flanges are both 80 meters per second, which really means that the pipe diameters at the exit and at the inlet is exactly the same. It is given that the motor that drives this pump delivers 40 kilowatts of power at a speed of 900 revolutions per minute. Now, it's also given that when the pump is filled with water but not turning, the vertical reactions at C and D are measured, and they are found to be both 250 newtons. It's then further given that the tensions in the pipes at A and B are exactly balanced by the forces due to the static pressure. In other words, we have a static pressure when the water is flowing through this. We have a static pressure at D, and the static pressure in D would tend to open up the flange connection. And of course the bolts in the flange connection, which are not indicated, will try to prevent that, but the force in the bolts, the tension force in the bolts, and the opening up force from the pressure at both B and A are exactly in balance. In other words, this means we do not have, if we consider the pump between the flanges at B and A, and above the reaction or the mountings at C and D, and with a cut through the shaft between the pump and the motor, if we consider this as our system, our reference volume, then it means that we do not have any horizontal forces acting on our system at the flange B or at the flange A, because of the fact that the tensions are balanced by the static pressure forces. Also, they tell us that we can neglect the shear forces and the bending moments in the pipes at the flanges B and A. Quite often what is done in pump installations is, and this is not shown in this specific case, but you can imagine that you may have something like that, is they put a piece of pipe at a connection that is almost like a concertina or a bellows. These bellows sections of pipes prevents any transmission of shear forces or bending moments from the outside pipe system to the pump. So you can imagine that we may have a concertina or a bellows thing around here to prevent, to make the bending moment zero and to make the shear force zero, and likewise at point A. So we don't have any shear forces at A and B, which really means that no forces are carried between the piping system and the pump at the flange B, and neither at the flange A. And then what they ask us to calculate is what are the vertical reactions at C and D while the pump is running. So when the pump is stationary, those are both 250 newtons, but the question is, what are those reactions when the pump is running? Now, let's start off with a volume flow rate. That is 20 cubic meters per minute. So to get that in cubic meters per second, we need to divide this by 60, so it gives us 0.3333 cubic meters per second. And if we then, from this, calculate the mass flow rate, we need to multiply the volume flow rate through the density of the water of 1,000 kilograms per cubic meter. This gives us a mass flow rate of 333 kilograms per second. And now you can imagine 333 kilograms is quite a mass. Every second, this pump is pumping this mass of water. Now, the exit and inlet speeds were given as 18 meters per second. Furthermore, the vertical reaction of the pump when it's not turning implies that the weight of the pump casing and the water is 500 newtons. And the fact that the reactions at C and D are exactly the same also implies that the center of mass of the pump is on the shaft, right in the center. Now, it's given that the motor is giving 40 kilowatts, and from this and the speed of the motor torque is calculated by saying that the motor torque must be the power in watts divided by the speed in radians per second. Now the speed is 900 revolutions per minute, so multiplying with 2 pi gives me, not revolutions per minute, but the radians per minute, and then I divide that by 60 to get it in radians per second. So dividing the 40 times 10 to the 3 watt by this speed in radians per second gives me a motor torque of 424.41 Newton meters. Now, where do I get this? We are at this point assuming that you know this, but let me just, perhaps you don't know this, or if you have seen this before for revision, let's just consider this for a moment. If I have a force that is moving through a displacement, and let's say the force vector and the displacement vector are perfectly aligned, then I can say that the work that is done by this force, U, is simply the magnitude of the force multiplied by the displacement of the force. You all know this. Now what I can also say is that the rate at which this force is doing work, which is really the power supplied by this force in watts, joules per second, P, that can be calculated as the force times the velocity. In other words, the time derivative of the S, or S dot, is the velocity with which the force is moving. Provided, of course, once again, as we've said there, that the direction of this force vector and the direction of the velocity vector is exactly parallel to one another. Then we can do the scalar calculation. And you can see more about this, although in vector form, with the dot product in equation 312 in Merriam and Craig. But so the power of the force is the force times the velocity of the point of application of the force, provided that they are parallel to one another. Now, when we talk of the same two equations, but not in terms of forces and displacements, but rather in terms of moments or torques, and the angle through which a torque acts, a torque which is displaced with the angular displacement also do work, and the work of such a torque can be simply calculated as the product of the torque with the angle through which the torque rotates in radians. So that is the work done by this torque. And in the same way that we went from the work equation to the power equation, we can do that the same here. The power of this, that is, in other words, the rate at which this moment M, or this torque M, is doing work, is then simply given as the power P is the torque multiplied by the time derivative of theta, the rate at which the angle changes, which is the angular velocity, omega. So this is the equation that I'm using at the top here. If the power is the torque times the angular velocity, the torque M can be calculated by dividing the power through the angular velocity in radians per second. So that is how I calculated this motor torque. Now, I'm assuming that this motor torque is applied to the system through the shaft. This is a logical explanation. In other words, we consider the motor itself to be not part of the system. We've made a cut through the motor shaft between the motor and the pump, but the motor is applying a torque through that shaft, and the torque is the value that was calculated here. So this allows us to now draw a free body diagram with all external forces and moments indicated. So it's perhaps not a very neat diagram, but I'm sure I'll be able to convince you that we can use it. This is the flange B, and its center is seen to be 0.075 meters below the point O, as indicated there. This is the flange A, and its center is 0.2 meters above point O, where point O is the center of my shaft. And by the way, I've added the axis system, horizontal x-axis to the right, the vertical y-axis vertically upwards. Now let's assume this flange A sits a distance L sub A to the right of point O. In other words, its x-coordinate is L sub A. And let's assume that the x-coordinate of the center of the flange at B is minus L sub B. In other words, this distance is the distance L sub B. I think that much that's essentially all I need to say here. Then I have the weight of the pump, and the water in the pump is 500 newtons, and it works right through the center. That was calculated a few slides ago. It was based on the fact that when the pump is not spinning, the reactions at C and D are 250 newtons each. So the weight must be 500 newtons downwards. And now, of course, this picture depicts while the pump is spinning. So now R sub C, the reaction at C, and R sub D, the reaction at D, are no longer 250 newtons. They are unknowns. That is exactly what we'd like to calculate, but we can fill them in as unknowns. And then the only other external force, it's really not a force, it's a torque, but it's a generalized force, is the force in the direction of rotation as indicated by this green arrow. In other words, clockwise, and its magnitude is the 424.41 Newton meters as calculated at the top. So this is my free body diagram, and it shows all external forces and moments in this red arrows. So I'm going to apply equation 419 to solve this problem. I'm going to take moments about the fixed point O in the center of the shaft. And I'm going to say that the sum of all moments about point O on the left-hand side must be equal to the mass flow rate M prime times the moment of the exit velocity about point O minus the moment of the inlet velocity of point O. And to calculate these two moments, I need to calculate the vectors D2 and D1. And let me just draw in these vectors. The vector D2 will be the vector ending right at the center of the exit flange measured from point O. So that red arrow is my D2. And I see that my D2 is plus LA, L sub A in the I direction, plus 0.2 in the J direction as indicated here. It's plus LA, I, plus 0.2 J. Then my vector D1 is the vector ending at the center of the inlet flange and starting at point O. And I see that this vector is minus L sub B in the I direction, and then minus, I need to measure from point O, minus 0.075 in the J direction. Remember that I'm measuring from point O, not from the point up there where I actually started pointing initially. So it's minus L sub B, I, minus 0.75 J. So there are my two vectors, D1 and D2. So if I now calculate my right-hand side of equation 419, I have the mass flow rate, which I've already calculated as 333.3 kilograms per cubic meters. and then the D2 cross the 18I exit velocity, minus, and then the D1 cross the inlet velocity of also 18I meters per second. And if I now calculate these cross products, I see that the unknowns L sub A and L sub B falls away because they both are components in the I direction crossing a vector in the I direction. And the cross product of these two I direction vectors are 0 in both cases. So it means that these dimensions L sub B and L sub A does not really play a role. It really means that I could have simply said that the moment arm of the, let's say the moment arm of the exit velocity is simply the 0.2 that I have here, and the moment arm of the inlet velocity is merely the 0.75 that I have here. That's just another way of doing it. In other words, I could have solved this as a scalar without using the cross products, but just using the moment arms, the distances at 90 degrees to the vector, between the vector and the point about which the moments are taken. So in any case, if I do use the vector method and then calculate these cross products, I end up with a single vector, a single resultant vector on the right-hand side of minus 1649.8 K. Of course, the K vector is coming out of the screen or out of the paper. In other words, it's anti-clockwise. So my right-hand side of the equation gives me a vector that is actually clockwise, and because of that, it's minus K. If I now look at my, okay, I've just repeated this on this slide. If I now look at the left-hand side of the equation, at the sum of the moments, I'm calculating the left-hand side. So for that, I'll have a moment of 424.41 Newton meters, also in the negative K direction, because remember the positive K direction is anti-clockwise, and this moment is in the clockwise direction, so it's minus 424.41 K. And then I see that the reaction at C, the reaction at D is giving me a positive moment, so I'll have the reaction at D times its moment arm is 0.15 meters in the positive K direction, and then the moment of the reaction at C is also giving me a clockwise moment, in other words a negative moment, so it's 0.15 times minus RC in the K direction. So this, these are all the moments of all external forces acting on my system about 0.0. So I can equate all of this to the value that I've calculated for the mass flow times the difference in velocity moments. And if I do, I can then, of course, then multiply or calculate the dot product of the whole equation with K to get rid of the unit vectors K. And I end up with this equation. And I have a second equation which simply comes from applying equilibrium, the equilibrium condition in the Y direction. There's no dynamics in the Y direction. There's no moment, there's no linear moment, linear momentum change in the Y direction. So in the Y direction, we can solve a problem of statics. So we can say that the sum of all forces in the Y direction must be 0, which means that R sub C plus R sub D minus 500 newtons must be equal to 0, which is the same as saying that R sub C plus R sub D must be plus 500 newtons. This is my second equation. So I've got two equations in two unknowns, R sub C and R sub D, and from this I can then solve for R sub C and R sub D. We see that at C I've got a upwards force of 4.33 kilonewtons, but at D I've got a downwards force. In other words, at point D the mounting is actually pulling down on the pump with 3.8348 kilonewtons. And with this we have solved the problem, and this is then also the end of this lecture.